Hi, I'm Toby Jackson. I'm a postdoc at the University of Cambridge, and this presentation is about gaps in forest canopies. So why should we care about gaps? Essentially because gaps are where lots of ecology happens. So gaps are the signs of recent disturbance. When a tree dies and falls over, it leaves a gap. And so the number of gaps tells us something about the rate of disturbance, and so therefore about the carbon balance of that forest. So they're important for that reason. Also, gaps allow light to reach the understories. And in dense forests, this is where most of the growth happens, or this is where a lot of the growth happens. So yeah, lots of ecological processes in forests happen in the gaps. So this is why we care. And in this presentation, I'm going to talk about the gap size frequency distributions. So that's essentially the ratio of small gaps to large gaps. We're going to be using airborne LiDAR to look at these gaps. And the main aim of the presentation is to try and interpret, or at least think about how we could interpret the observed gaps. So as we'll see, it's very easy to observe gaps, but it's quite difficult to interpret them. And so the way I'm going to try and do that is with a series of model experiments, which we'll get to. So to start with, here is some airborne LiDAR data. So this is a canopy height model for Barro Colorado Island in Panama. And the green represents the higher heights. So these are tall trees in green, and the red are the gaps. So with airborne LiDAR data, it's very easy to see the gaps. And in the figure in the middle, what I've done is essentially delineated all those gaps which reach down to 10 meters. So you have to define what you mean by a gap. And essentially I've defined for this figure, it has to reach from the top of the canopy down to 10 meters. And then on the right, what we see is the area of these gaps in meters squared against the number of them. So this is our size frequency distribution. And what this is showing us is that there's a lot more small gaps than large gaps. So down here, there's only one gap, which is around 1,000 meters squared, but there's 100 gaps, more like 30 meters squared around. So you should note that this is on a log scale. And so a fit line here represents a power law. And that's the equation we have up here in the middle. And so the number of gaps is essentially proportional to the area of those gaps to the negative alpha. And this parameter alpha is going to be very important today. So please remember, this parameter alpha is the exponent of this power law. And I'll come back to that. So this slide shows some work that I've been doing with Cristiano. And what he's done is taken some amazing LiDAR data, which has been collected over the whole of the Brazilian Amazon, and extracted the gaps, and then calculated the fitter power law, and calculated the alpha value. And so these points show those alpha values. So over here, we have alpha values have less negative alpha values, so a less steep slope, and so therefore we have more large gaps in this area. And then over here we have more negative or steeper slope, and therefore more small gaps proportionally. So that's an interesting trend, but it's quite difficult to work out what it means. So the aim of this presentation is to propose a way of untangling this using model experiments. So for model experiments, we first need a good and representative model of the canopy. So here in the top left is the LiDAR data again. So this is our data, our observations that we're trying to model. And then here, the next one is a simple model of this forest using the inventory data. So this is Barro Colorado Island still, which is probably the best studied tropical forest. And it has really good inventory data. So each stem is mapped, so we know the size and location of each stem. And there's a very good local allometry from Cano et al., which is the name on this graph. And essentially what I've done is applied those and simulated the canopy height model and then calculated the gaps. So that's quite good. But essentially what we were finding is that there's far too many gaps at most heights in this simple model. And so we needed a better model of forest structure. And so for that, I enlisted the help of Fabian, who has created the Canopy constructor, the CC in these titles. And so the Canopy constructor can be run in two ways, but both essentially use the LiDAR data to choose a model which best fits. So it uses the inventory data, the height allometries, the crown allometries, just as before, but now it also uses the LiDAR data. And the random fits version just tries to find a model which represents the canopy height distribution as observed in the LiDAR data. So this doesn't have quite the same arrangement of crowns as here, although it has the same arrangement of stems, but the overall canopy height distribution is similar. But then the spatial fit actually exchanges crowns between trees. So two trees of similar sizes could have quite different crowns because of the uncertainty in the allometry. And in the spatial fit one, it shifts around those crowns between trees to better fit the actual spatial variation observed in the LiDAR. So we have three models of the forest structure, and then we want to look at the gaps. So what we see straight away, as I said before, is that there were too many gaps in the simple model, and then that the two canopy constructor models, the random fit overestimates the number of gaps and the spatial fit underestimates. So they're both sides of it at most heights. So then in this one, here is our alpha value. This is the exponent of our power law. I think the very important one that we need to remember. And essentially the simple model overestimates the exponent slightly, but this being a power law, it's an important overestimation. Whereas the ones from the canopy constructor do rather better, especially in this kind of range. Okay, so for the rest of this presentation, I'm going to use the two canopy constructor models because there are some interesting differences between them. And I'm going to choose a cutoff height of 10 meters. And I just keep that constant throughout the rest of this presentation. So what we do next is we run some model experiments. So we use our two models and we change the parameters. So in this case, it's our baseline. We've cut 20, 30, 40% of the large trees out. So you'll see these GIFs. What happens is essentially we start from the baseline and we just cut trees sequentially. And so this is to simulate disturbance. And it's only the large trees that we cut. And so what you see in terms of gaps is the number of gaps increases. And that's exactly as you'd expect because there's more gaps where the trees have been cut out. And also more interestingly, the alpha value decreases, which essentially means there's more large gaps as we cut out more trees. And that's again, pretty expected. But the good point here is that both simulations show the same thing. So we're pretty confident this is what happens when disturbance occurs. So that's simple enough. So then, therefore, if you, this is useful because if you observed a forest and you calculated the alpha value and the number of gaps, and then you calculated again sometime later, you could see whether disturbance has happened or not using this pattern. The next parameter we looked at was the height allometry. And we found a really interesting pattern here. Essentially, both simulations, both the properties of the gaps were insensitive to the height allometry. So the actual, the x-axis here is the height of the largest tree in the plot. And it is around 40 meters. This is around the baseline in BCI, in Barrow, Colorado Island. And so if you increase the height of the trees, not much happens. And if you decrease the height of the trees, not much happens either, except when you get to this range. And this is because the trees lots of the trees are now below our cutoff height, which we've defined as 10 meters. So it's kind of a trivial point, but important to know that tree height alone doesn't make much difference. Now things get complicated, and so what we've done here is change the crown allometry. So again, the x-axis on these graphs is the crown radius for the largest tree in the plot, and that's around 20 meters. And so this is it's around this point in the GIFs is the baseline, and so the trees grow larger than that. And so they start off really small, they come to a reasonable level of crown radius, and then they grow larger. And so we see the effect of that on the gaps. And what we see essentially is that the number of gaps decreases as you increase crown radius. So that's to be expected because the crowns essentially take up more of the space. But actually, if you look at the alpha, we have some really interesting things going on here in that our simulations, our forest models go in different directions. Okay. So why is this? So let's first start with the random model. So in this one, the crowns are just placed according to their allometry and with some variation. So there's no spatial aggregation of crowns. So there's that means that there's quite a lot of gaps around the crowns. So we see that there's more gaps in the random simulations than the spatial one. And therefore, when you increase the crown radius, you actually the crowns grow into those gaps. And so the number of gaps decreases quite fast, and the gaps which are remaining become smaller. So that's why the alpha goes up. And the same happens in reverse. When you decrease the crown radius, you get fewer gaps, and they are generally larger. So the random one is quite easy to understand. But the spatial one, which was our best model, shows a much more complicated pattern. So when you increase the crown radius above the baseline, not much happens to alpha, essentially. The number of gaps decreases slightly, but the size of them doesn't change very much. And this is because in the spatial one, in the baseline, the trees are spatially aggregated. So you have clumps of tall trees with large crowns next to each other, filling space accurately. And then you have areas with low canopy height where there are already gaps. And so where the trees are filling space quite efficiently, this increase in crown radius just causes them to grow into each other. And so they don't really change the gaps very much. So this is why we don't see much change in alpha and why we see a less steep slope over here. And then the same logic explains what happens in the reverse. So because these trees are spatially aggregated and filling space accurately, when you mess with that and reduce the crown radius, loads of gaps appear really quickly. And these tend to be quite small gaps in between crowns, and so you see the alpha goes up. And that's why this rises so steeply here as well. The number of gaps increases really quickly if you change from the baseline. So to sum up, gaps are ecologically very important and they're easy to detect, but they're quite hard to interpret. Tree height doesn't make much difference as long as you've chosen a good cutoff height. But crown allometry and the spatial arrangement of trees are important. And that means that comparing gaps across different forests observed from airborne LiDAR, say, across a large scale, is actually quite complicated unless you know something about the structure of those forests. Having said that, the signature of disturbance is quite simple. Essentially, as you lose trees, you get more large gaps, and so alpha goes down. And as a side point, we found during the study that simulating forest structure is actually surprisingly difficult. So even with really good high quality input data, we couldn't accurately reproduce what we observed from the LiDAR. So we had to use the Canopy constructor and fit it to the LiDAR. So with that, I'd like to say thanks for listening, and I'd be happy to answer any questions.